And today I'm going to talk about content-based image indexing for biomedical image databases. Here's a brief overview of my presentation. First, I'm going to give a brief introduction to content-based image indexing. Then I'm going to describe its applications to biomedical databases. I'm going to just list some relevant literature, describe some current research and development in the area, discuss some open problems, offer you my insight and reflections, and of course, a list of references. So first of all, image indexing. Indexing is a technique used by database system management to pretty much speed up particular kinds of queries. Well, we do index textual information all the time, so why is there a need to index images? Well, first of all, huge volumes of images are produced every day. And because due to such large sizes of repositories, retrieval of those images would be extremely hard if we didn't have efficient indexing methods. So content-based image indexing. When we talk about content-based image indexing, we first have to think about what is the image content. At the very primary basic level, image content can be divided into two categories. Low-level, iconic, which pretty much is texture, shape, color, contour, etc., and a high-level, semantic content, which is meaning of the objects and their spatial relationships. So content-based image indexing is indexing of images based on the automatically derived image features. There are several approaches to content-based image indexing, and they're all based on either different shapes, such as, or features such as histogram matching, color layout, region-based, texture-based, spatial similarity, and so on and so forth. So now we go into how does this all apply to health informatics area. Well, content-based image indexing plays a very important role in biomedical databases. In the medical field, there's images created all the time. And just an interesting fact is that the radiology department of the University Hospital of Geneva alone produced 12,000 images in a single day in 2002. So what is going on is that we have an increased number of digital imaging modalities. We're having MRI, CT scans, histology images. It's followed by different multimedia types. We have different images represented in different formats. And all this results in more complex medical databases, which means more complex image indexing methods. First of all, what is going on currently? Well, currently, indexing is mostly done by patient's name and diagnosis. As Tagar and Company states, such indexing techniques do not take advantage of exploring image collections on the basis of images that possess similar appearance. Clearly, content-based image indexing is needed to enable such explorations. Who benefits from content-based image indexing? Well, content-based image indexing is used in several contexts. It's used for clinical decision-making processes. It's used for pathology detection. And it's also used for educational and training purposes. We browse medical image collections not only to discover certain lesion or pathology, but also to educate and train future physicians, nurses, and other healthcare providers. Another issue is that content-based image indexing is a complex issue when it comes to biomedical domain, as opposed to other domains such as technical or industrial, because of the sensitive nature of the field of medicine itself. What I mean by that is, what makes it so challenging? Well, first of all, it's global versus local features. In an image, we can look at the image globally and say, okay, this is a lung, or we can look at the very local features of that image, such as very small regions which may contain lesions. This makes feature extraction hard because you don't know, are you searching for a global feature or are you searching for something that's regional? Also, two different doctors won't interpret every single image the same. They might look at the same radiograph, and one would come up with one diagnosis, another doctor can come up with another diagnosis. So diagnostic images lead to observational findings that not necessarily can be agreed upon by all observers. Also, medical knowledge is often imprecise and ill-defined. And as such, it's very hard to extract from images. And also, different types of images resulting from diverse technologies. We have photographic images, we have radiographic images, we have tomography images. And just to show you how diverse these images can be, we're having here just a couple of different images. But even within histology images itself, oops, these two images belong to the same class, but they're not visually alike. Also, we have CT scans and MRI scans that are two different types of images, but are very similar in appearance. Here is the review of relevant literature. Content-based image indexing has been a hot field for the past 10 years, and there's a lot of research going on in this area. This review is primarily concentrated on biomedical domain. And what is going on is pretty much, to form an index, you need to detect and represent features of medical images. And most research nowadays concentrates on image content, such as shape, texture, color, contour, or, for example, wavelet. Nala talked about it too. But just one example, this is a content-based image indexing and searching using Debuchy's wavelets. And it's pretty much an indexing algorithm based on wavelet transform. Here we have a content-based image indexing algorithm that's based on metric histograms. There's some that are based on a region-based indexing. This one is using KD trees. This one is based on texture. However, this is just an example of region-based indexing. And what's going on here is that images are partitioned into meaningful regions. And so here we have an image. We do region segmentation on an image, and we extract the desired region. And this region is then indexed into the database. Current progress, I would like to talk about two studies. I chose this one because it doesn't really talk about application to medical area per se, but to application of content-based image indexing everywhere. And this one is really domain-specific. It's content-based 3D image indexing of neuroradiology images. The first one is indexing using wavelets. What's happening here is that image is partitioned into blocks, and then average color of each block is stored. And how's that happening is that you have an image, it's overlaid by a 100 by 28 grid, and then each point on the grid corresponds to one point on the image, and then the average color is calculated. Indexing algorithm then applies the wavelet transform, which is pretty much just two filters, low and high filter, that filter these pixels. And the wavelet coefficients in the lowest few frequency bands and their variances are stored in a feature vector. And feature vector is what is used for indexing. And these are chosen because of the algorithm. It's proven that by this algorithm, the lowest frequencies contain the most information. However, major drawback of this content-based image indexing technique is that it's very sensitive to rotation, scaling, and shifting. This is just the illustration. So here we have an image, which is then pre-processed. Then we do a wavelet transform on the pre-processed image. And after that, a feature vector is created. And this feature vector is used to index into a database. This is another content-based image indexing technique, and it's used in neuroradiologic image indexing. And in this technique, each image can be viewed as a data point in some multidimensional feature space. And I chose this study because it really highlights how important it is to define a feature set when talking about content-based image indexing in biomedical databases. In order to index something meaningfully, you have to have a predefined set of features by which you want to do indexing by. In the following study, the following visual features have been considered. One is mass effect, anatomical location, density, contrast, and boundary. And all of these have been, because we're dealing with 3D CT scans of brain, they pretty much have something to do with brain structure. So what's happening here is, the basic idea is to build a set of feature detectors which can capture all the values previously listed. So what's going to happen is we have a 3D symmetry plane detector, lesion detector, mass effect detector, and an anatomical location detector. The first one will just, normal brain has approximate bilateral symmetry. Pathological brains lack such symmetry because either lesion is present or there's swelling in the brain. So if a feature detector extracts such a feature, which indicates a pathological brain, it would move down next to lesion detector, which would then go to mass effect detector and then calculate. At the end, you'll find the 3D position of the lesion. And this is just an overview of how it happens. So all of these detectors, feature detectors, detect features, which are listed here. And based on these features, weights and confidence is calculated and image index is created. Current research and development, there's a lot going on. This is just a very short list of just diverse applications. What are open problems in this area? Well, defining appropriate feature detectors and that will be used for index creation is a hard problem because every medical imaging domain has different needs. So different features may be okay for cardiological images, but might not be so okay for brain images. Also, efficient image indexing, not only for pathology, but also for educational and training purposes is needed. Currently, most indexing schemas index images solely for pathological pathology detection. And there's a growing need for indexing images based on the content, not only for detecting pathologies, but also for educational purposes. Open problems also is different technologies produce different types of images. So, and currently there's no generalized image processing tool that will allow indexing based on key feature extractions from any image. So right now we can do efficient indexing in a certain area. We can do it for brain, we can do it for histology images. But let's say we want to have a database of all diverse images. It's not going to happen because it won't know how to index it. And a very, very, very important thing is integration into PACS. Indexing techniques and algorithms should be easily incorporated into PACS. And also development of indexing techniques for higher dimensional medical images, such as 3D or 4D, are needed. Also, maybe a development of a text content-based indexing hybrid, which would allow not only indexing based on content, but also based on text. And also, there's no systematic comparison of any of the methods that are used for content-based imaging. And also, measures have not been developed. So even if you do develop an indexing algorithm, there's no evidence of how it actually acts. Some insights and reflections. Content-based image indexing has great potential to improve healthcare, and as well as it also has great potential to improve education and training of physicians, nurses, and other healthcare providers. However, in order to do so, sensitive content-based image indexing techniques must be developed. Indexing based solely on a certain set of image features, i.e. texture, shape, color, it's not precise enough. And image feature extractors need to be used in order to define an appropriate set of features. Also, indexing images based on multi-level feature sets, indexing of images based on a lot of features as opposed to indexing solely based on one feature is very important because it's going to enable semantic interoperability. What does that mean is that hopefully, if this is possible, one day we're going to be able to query not only image from one database, but an image across a several set of databases. And also, several limitations of this area are that it lacks actual implementations. Many prototypes, not many implementations. Not many projects have been used widely in clinical settings. They have only been kind of like text models. And also the lack of documentation of evaluation of current technology. So even if you do have an indexing schema, there's little evidence to say how successful it is and if you can extend it to a different area. And these are my references, and that's just the beginning of the list. And if you have any questions. Oh, they do. Actually, if I go, I'll go on to one of the slides because there's a very interesting comment regarding that. I should have just gone to go slide. But what's happening by Digicom standard, there's already metadata included into an image. But entering metadata, you have to do it either by human or by a machine. And that's susceptible to error. And it's actually there's a study done on, and it's a 15% chance of error. That the data that's entered into, I have it and it was kind of blocked out. But the data that was actually entered into an image as metadata has been wrong. And it's actually wrong by 15%, in 15% of the cases, which is a pretty high error, especially if we're talking about clinical diagnosis. I'll find it. Oh, there it is. It says beneficial to find images of the same modality, same anatomic region of the same disease. This information is already integrated into Digicom headers, so there is metadata. However, error rates are at 16%. So as long as the moment you put a human into the loop, the error rates kind of shoot up.
When we were talking, initially you had looked at image recognition algorithms, and we talked about sort of lowering the threshold a bit and looking more for features. Yet it seems like that's a big part of it. In other words, what you want to do at the end of
exactly.
it seems like you come to the conclusion that we need to have the image recognition algorithm
in order to get indexing, because it doesn't seem logical to index something if you're only going to index it based on color, based on shape, based on texture. Because we're talking about medical images; they're so fine in detail and they're so sensitive. And pretty much the differences between the two images are minuscule. It could be just a millimeter in between two vertebrae. So you need to develop sensitive methods that would detect these features, because you can use just a simple indexing mechanism, and then when you try to retrieve something, you're going to get a lot of things that you don't need. So the success of an indexing schema is how well can it index based on the features that you want it to index on. So even though I tried to stay away from it, it just seemed like indexing is so closely related to image retrieval that it wouldn't make sense to have indexing if it weren't in the context of the retrieval.